All right. App School, successor to Lesson 0 being Lesson 1. So I guess in the Urbit sense, we have proceeded from truth to error, perhaps. Um, Last time, you started to run into some of the interesting ideas around how Urbit thinks of organizing user space. Like what is an agent? What does it mean in an immutable functional as in language operating system like Urbit to operate on particular values and update the state and replace it going forward. And so the technical tooling that was used to accomplish this is to use a door and to simply pass the current state of your object in as a door, in as an argument, as the sample to the door every time you want to interact with that door. And so all of this is maintained by Gall, which keeps track of, has a list of running agents. Every agent has its state, and it has the corresponding door against which that state is applied every time someone wants to run something in this system. So you get this really nice partition of state being, the kind of thing that you're carrying around. It's the data, and then the active code that you're building to try and operate on it. Now, ultimately, with App School, we want to build things that are non-trivial, right? We want to be able to build apps that do more than simply respond to poke. So we're going to have to look at subscriptions and how apps update each other, how data are returned, and so forth. In the first place, though, we need to spend a little bit of time looking at Arvo, which is, of course, the Urbit operating system. Sometimes you'll hear people talk about user space in Urbit and then contrast it to the kernel. And there are some differences in the way that code evaluates in both of these contexts. For instance, in user space, you can run code that crashes and it doesn't take down your ship. In kernel space, you don't want code that crashes because it'll actually take down your whole ship. There's some other differences that arise from this development as well. But in user space, one of the nice things is that we have this scaffolding that makes it possible for us to handle crashes, handle errors, and so forth, and still build and do useful things with our code as we're proceeding, right? So if a poke crashes, it doesn't take down Gall, it doesn't take down Arvo and everything else. Now, we would like to take a look at Arvo and see what Urbit as an operating system can do for you. So if you think about, a traditional operating system, like a Windows or a Mac or a Linux, what sorts of things does that operating system do for you, right? Like why bother? Why have an operating system at all? That's not just rhetorical. I'm actually interested in comments there. Like what does it do? Why do we care about having an operating system?
Why do we care having hardware?
I don't know. Why do you care having hardware?
Yeah, because else my programs would be just written in paper and not operating on the real world.
Yep. So at some level, the operating system gives you a way to actually evaluate a program. You can hand it a program and it'll like we talked a little bit at the beginning last time, you have like an ELF executable format or like a Java executable format, other kinds of things. And it defines the sort of standard way of running this program. In the comments are suggested multiple processes. So the idea that you can actually run multiple programs and switch through them somehow, either single threaded preemptively, where you're kind of running part of a program at a time and then switching programs quickly. This is like old school Windows 3.1, or actually parallelizing your processes, providing standard interfaces to your hardware, which can mean a lot of things, right? It can mean like, can you talk to your keyboard? Can you talk to your monitor? But it can also mean things like, what does your RAM memory layout look like? Right? How does your hard drive work? How does your hard drive store the information that you're doing? Yeah, provide a cathedral of stability for a bazaar of user space stuff. Yeah, in a sense. And so the operating system is essentially sort of the service manager in this whole context. As is also pointed out here, it allows us to think of hardware and software as different things. It allows us to sort of abstract at different levels as we run different programs, different processes, and what's going on. Now, Urbit has described itself variously in the past as an operating system or an operating function. It is an operating system, but when I use that phrase, I describe it to people as I call it an L2 operating system. So if you're familiar with blockchains, an L1 is something like Ethereum that directly defines its own protocol, like Ethereum virtual machine. And an L2 is something that runs on top of Ethereum, using Ethereum as kind of running as a kind of a meta protocol above Ethereum. So right now, Urbit runs this way. It has its own concept of kernel and user space, but the runtime layer that actually evaluates the knock that you produce and deals with Arvo and your system calls and everything runs on some other operating system. We don't yet have a runtime that runs on bare metal. People have talked about that kind of as like a research project, for instance. And so when we're going to run user space code, one of the things that we need to know is, what does Arvo actually do for us? Why do we care, right? Like at core, what does Urbit as an operating system do besides run Hoon? At this point, basically, we've run Hoon. You ran through Hoon school. You've run generators. You've done some basic Gall agents now. But for the most part, you haven't really done anything other than just write a script, run that script. So what else is available? What else can happen here? Now, you're probably familiar. Let me share the screen here. And all right, it's going to give you those little black boxes in the corners, and we're just going to have to live with that because that's what Zoom does for us. At least I can move things out of the way. All right, that look okay? We'll live with it. All right, so at its core, well, I'll give you this diagram first. Now, at any point during this, pop in with questions, because I'm just going to sort of sequentially talk through what Arvo is, what Arvo does from the inside out. So we have this, okay, no diagram. Can anyone see the diagram? Okay, we've had this problem before where some people can see the shared screen and a few people cannot. I've never found a good solution for why that happens, but it does happen sometimes. It's a recognized problem. All right, so at the innermost part of this, I have this little key-shaped structure here. We're going to call that knock, which is what the system actually runs. Arvo is, strictly speaking, it's an event loop. Basically, it's a processor that receives an event. We haven't really defined an event. Well, it receives a move, and then it processes this move and converts it into an event and updates the state of the system. So it maintains this notion of like what my current system state is. And that system state is the end result of running all of the previous events up to this time. So for instance, if your Urbit ship crashes, occasionally one of the solutions that you need to try to fix it is you need to do an event log replay. And what that means is you actually start your ship from zero, or with the newer Urbit peer chopping stuff, you can start later, and you play back the events that reproduce what is the current state of your system. So Arvo itself And this inner circle here, this little blue line, doesn't really do a whole lot. It's not a particularly large file. The only complicated thing about Arvo is results from the fact that Arvo has the ability to upgrade itself. And so there's kind of some complicated pieces that make it possible for Arvo to sort of half load itself and then use that to fully upload itself. So if you pay attention when you receive an over-the-air update, you can see in the log messages some of what's going on here. All right, question here in the chat. So a move is the type of a message to Arvo. What is an event the type of? So an event is essentially the result of that. In Urbit, inside of Urbit, we don't really look at events. Events are sort of like the things that resulted in where we are now, right? So if essentially what happens is if you have a move, for instance, this is like typing an expression in at the dojo prompt and pressing enter. That expression, the request to evaluate that expression is sent to Arvo. And if it crashes partway through, then no event is generated and the system state is not updated. So you may see in the terminal output, you may see a crash message and so forth, but it doesn't actually change the internal state of your Urbit ship. So in a sense, Urbit, in the sense that you're in the present, you're in the state right now, actually doesn't know about events. Events are simply the things that the event log is the history of things that led you to the state you're in right now. And moves are things you submit, you create and you submit. And if they evaluate correctly, it updates your state, but you still sort of only know the state where you're at right now, which is kind of this interesting perspective on what's going on. Like Urbit is very presentist in this sense. The diagram here that I should explain a little bit. So this has knock at the center, and then I have this kind of the C shape around this key, this green key. I'm going to call that the runtime. It's just a heuristic representation here. So you have a runtime that runs knock. Then you have a set of what we'll call inner cores, which are Arvo. There's a number of cores that are generated by Hoon, which are the actual language, the parsers, some of the other tooling that's out there. And then there's Lol and Zeus, which are essentially standard library headers. So like JSON parsing, other kinds of operations live here, for instance. And then outside of that, you have what are called the veins. And that's this outer circle here. The proportionate size of each one of these is the number of lines of code that these actually consist of. And so you can see that some veins are large and presumably complicated, like Ames and Clay. So Ames handles our networking, Clay handles our file system operations, Error handles other kinds of, it's our HTTP server vein. Those are quite large and complicated. Some veins, like Bane, which is merely a timer vein, or Dill, which processes keystroke events and manages terminal sessions, are quite simple. They don't really have a lot to do, and they're rather small files. And it's not clear that they would really ever need to be any bigger to do what they need to do. So when we talk about kernel space and user space, this basically lays out sort of taking that diagram that I had and kind of turning it sideways. You have Arvo and Knock and the runtime over here on the left. Then you have a number of kernel veins, and each one of these kernel veins does something specific for the system. And this is mostly what we're going to talk about today. Today's kind of the talkiest bit of App School, but we actually need to look at this. So like I say, feel free to ask me questions and interrupt, because I'm happy to go into detail on what's actually going on with these. Gall is our user space agent. It's our app manager. And so if we're running particular agents inside of this, looks like the white on yellow isn't quite as visible as I would have hoped. Docket, Treaty, Hood, Dojo, I guess no longer Graph Store. I can update this graphic. If you're running the Bitcoin wallet, if you're running Spider, which is a thread manager, if you're running Portal, if you're running Talk, Groups, whatever else, these are running agents inside of your system here. Generators live in user space, for instance. Threads, you probably have not used threads very much yet. We will talk about them more in, I think, 3 or 4 more lessons. We're going to build some threads. I will actually talk a little bit more about threads today. The problem is actually threads is a terrible name for what they are. That's kind of universally agreed. All right, let me get my chat back up here just so I can monitor what's actually going on with you all. All right, let's see. All right, so there's a lot of veins. Let's see, I guess we talked about the runtime, we talked about the event handler and these things. Then there's a lot of veins, and we're going to spend most of our time talking about veins. What do veins do for us in these particular instances? So here's a little bit of terminology. At this point, you do not need to sweat their terminology. Eventually, you'll get to the point where you need to start distinguishing these things. But for the most part, these things are you need to know pass and give, because pass means you're sending a move out to a different part of the system. Essentially, you're making a poke or a request somewhere else in your system. And then that part of the system gives you back a response optionally. Not everything that you pass will result in a gift, result in a value back, but you pass something to another vein, and then Arvo handles the event and dispatches it to the vein. You know, it's like I say, it's kind of a multiplexer. It's a dispatcher as well as an event loop. And then you receive that value back. So this is going to be our operating model in what we do here. So for instance, when I run a command at my dojo, what I will do is I'll type in an expression, I will press enter, and then that expression as text that I typed is inside of Dojo, which is a user space agent, so it's running inside of Gall. So this message, this text gets passed to Gall, gets passed to Arvo, and then Arvo decides what to do with it. In many cases, what it needs to do with it is simply evaluate it as Hoon, which isn't even another vein. It's just part of Arvo. It just, evaluates it as Hoon and gives you this result back. But then the result comes back to you as a gift to Dojo, which then displays the output. So your life cycle is going to be, you're going to pass data somewhere, and then assuming you get something back, that will be received back as a gift. Don't sweat the terminology too much, but I will say pass and give a lot. Don't worry about note, task, sign, gift, and all these sorts of things. Okay. We could talk about scrying right now. Let's do it in this order, actually. Okay. So Urbit is a functional operating system. And that means that when I run code, one of the guarantees that Urbit wants to make to me is that code is that, if I call a function, it's referentially transparent. What that means, okay, that's a technical term, but what that means is that I should be able to take the output of a function, like the value that actually results, and every time I made that function call with those same arguments, I should be able to replace that value in. In other words, like everything is very predictable and has strong guarantees that it, if I run the same code twice, I get the same results. Now, if, for instance, I am loading a file from disk, do I have that guarantee? If I load a file from disk, do I have a guarantee that that file on my disk looks the same every time that I load it? Like, yes and no, right? So like in the classical sense of, I'm running Windows or DOS or, whatever I'm running, it does not, right? There's no guarantee that every time I open, readme.txt, it'll be the same content. What Urbit is going to do is whenever you can make that kind of request, we call it a scry or a peak. They've kind of gone back and forth on, are we going to call it a scry? Are we going to call it a peak? I think everyone's pretty much on the scry bandwagon at this point. And so it's an on-peak arm, but it's called a scry. And so a scry is a request for information, and we're going to pass two pieces of information to wherever we're requesting this from. One piece is the data type that we expect to get back. So, do we expect an atom back? Do we expect a cell back? Do we expect something complicated like a JSON back? And the other one is what we're going to call a scry path. And a scry path is a unique identifier that means that I actually can make guarantees about the contents of a particular file. So you've run into this before with generators. What happens every time you bar commit? So you have a generator, you make an edit to that file, you bar commit. What information does Dojo give you?
It tells you that the file has been updated.
Okay, tells you that the file's been updated. And as also remarked in the comment here, some kind of version bump. So putting those together, the way it's telling us that the file's been updated is that there is there's a number that's attached to the version of that file. Now in Urbit, we actually have an interesting phenomenon from a version control standpoint, which is we actually know we have all the previous versions of the file. We know the full history of this file as it has been part of Urbit. Which means you can get Git-like behavior, version control repository behavior for free using Clay today. There's actually there's an app workshop project you can look around and find if you're interested, called Pratt, where we do implement some Git-like functionality directly on top of Clay, like file diffs and so forth. But put another way, every time that version bump happens, what we're doing is we are binding that value into the scry namespace. Another technical phrase. The scry namespace is basically a unique tabulation of paths or names, labels, tags, whatever you want to call them, to resulting values. So you can think of this as a dictionary or a map lookup, where you have a key and you have a value that corresponds to it. And the guarantee of binding it in the scry namespace is that for all time, if you make this request, you will get this answer. And so this is how Urbit gets around the fact that, if you update a file, the file changes. Well, Urbit handles this by binding the value of a file at a particular time in history to a unique path, to a unique identifier. And thereafter, you can always access it through that identifier. So when we talk about scries, this is what we're going to do. Now, most of the time right now, when you've looked at scries, well, you haven't really looked at scries yet, but you can think about the only place you've seen this kind of information is with file changes. But it turns out we actually do this for all parts of the operating system. If you're doing a network call, other kinds of things, then we're going to be scrying into a value and getting that value back. If I want to know the current value of the list of pals that you have inside of your pals agent, if you've installed that, then I can access that at a unique path. And I'm guaranteed that as long as I access it at that unique path, I will always get the same answer. Now, most of the time, I want the last value, right? I don't want to know who your pals were on August 12th. I want to know who your pals are today. And so what we're going to do is we're normally going to make a scry request with a date as a value. And this just means give me the last value. Give me whatever the result was as of this date, the last value prior to this timestamp. All right, so let's actually, let's see. I want to share. this one. Okay, as soon as turn my chat back on. All right. Now, what I'm going to be able to do is I'm going to be able to say something like, this is going to be .cat. So I'm down here at the bottom in my terminal here. Well, okay, it's going to glue me to the bottom. All right. So .cat is going to be a scry. It means that I'm requesting information and I'm telling it, just lock this value in. And the first thing I have to give a scry is, some sort of way of getting this value back. So if I were to read a text file, for instance, then this would be organized as a list of pat-t, or a list of chords. I just happen to know this, right? Like, it's not a priori clear that it would be a list of chords as opposed to one gigantic chord, or as opposed to being a tape. But the default way this will come back is as a list of chords. So I give it a type, and then everything else that I'm going to give it here is going to sort of be glued together into this path. By convention, I'm going to give it a vein, in this case, clay. I'm going to give it a type, which can be a lot of different things, and particularly in clay. And X is generally just give me information, show me a value. In this case, it means read a file. So, if I'm on aims, we'll look at what all the veins do in a moment. But if I'm on aims and I do an X scry, then I'm just asking it, for information about a ship. For instance, if I'm in Gaul and I do an X scry, I'm asking it for a value like who are your pals? The other thing you might do is Y is kind of like, show me everything in a directory, show me everything in a collection. Those tend to be the two most common types here. So there's a vein, which is a single letter, A, B, C, D, and so on down. This is one reason that the veins all follow, they all have a alphabetical order to them. So that ASCII-wise, we can distinguish them from each other at this point. And then I'm going to give it the rest of the path. Now, by convention, we often use three tizzes, three equal signs here. By itself, let me just do this by itself. This returns a tuple. If I start with a FAS and I do three equals, then this gives me my current ship, my current desk, and my current timestamp. And what type are these values? Or what is something that starts with a sig dot?
It's not.
Yes, so this is a pat TA or a not. If I'm curious about verifying that, my dojo is at the bottom of my screen in the terminal here. Can you see that?
Yeah,
or is it
sorry.
Clipping weird? Okay.
Not my bad.
I can make it a little larger too, which might help. So we can verify here, yeah, so pat TA, and this is a list. Yeah, so there's a question, why is that a not and not a pat P? Because it's because a path is a list of text, right? Like it's a list of names. So on your file system, when you have a path, you're like Windows / program files / whatever, right? Like there's a name for a folder, name for a folder, name for a file, and so forth. We're kind of using it analogously here. So these are actually names, so they're the names as text. They're not the value that it would be if it were parsed as that value. And there are interesting things you can do here, like if you have something else here, like you want to talk about the rumors desk, you can replace one of these tizzes with that value. And so very often you will see people write things like this. And this means my current ship on X desk at the current timestamp. But they're all going to be text because that's what a path is. It's a set of text. Now this has a benefit, right? Which means that we are working on our current ship at our current time. So, if I were to say, lus cat tis gen ls hoon like this, that should work. It might take a second. Yeah, so it takes a second to spit it all out. And I could scroll up and maybe fit a little bit more on my screen, starting right here. But it gives me this information. So I actually could see, that should work. Yeah. Now I could try to do a different version of this if it's ever been changed. It turns out, this file has never been modified. I've never changed ls, and so there may not be other versions than the one that's there, right? Like ls1 is the only version that exists. I can't refer to another version. But in other cases, I might be able to. So that's what a path is. That's what this unique identifier is. Now, okay. So anyway, let's go back to, I was talking about dot cuts. Okay. So if I'm going to load a file, then I'm going to give it a type, and then everything else is going to be a path. And you'll see these paths, it's a list of text. You'll see them constructed in different ways. Most often people do a separate term, a TAS, at the beginning for what's called the scry type, which is the CX, and then they do everything else. But you'll see this built a lot of different ways as you go forward. So here, if I go gen ls hoon, I think it might not be happy about the hoon. Sometimes you can force these things. Let's see if it'll let me do it through a different mark. Hoon might actually be coming in as a chord. This is one place where the file ending actually, yeah, there we go. Okay. So this value here should work on your system without any changes there. So it loads the contents of the hoon file as a single chord, and then there's nothing else to do with it, so it just displays back to me. Now, what looks different about this? So what are these FAS0As?
Those look like new lines, or they should be new lines.
Right. So functionally, these are new lines. Now, if you've worked in other programming languages before, most programming languages do something like this, like FASN or maybe FASN, FASR for new lines. And this is like a special identifier for a new line. What Urbit is preferring to do here is you're specifying in hexadecimal the actual ASCII character code of that special character. So rather than say, okay, we have like an ad hoc, FASN and a FAST and a FASR and a FASV and, who knows what else, Urbit is just saying, look, if you're going to start something with a FAS, then you're specifying hexadecimal, 2 characters, whatever that value is. So that's why these show up as FAS0As everywhere that we see them here. Now, there's probably some interesting games we could play to see if we can get this to actually process those. Let's see if a SIGPAM would do it for us. No, see, SIGPAM even keeps it. Yeah, so it's kind of sticky in that it won't even process them as new lines. It actually it keeps the character, it hangs on to the character information for you in most output formats. we'd have to turn it into a tape and then do it through the formatted text stuff that's not in Hoon School. I think I moved that to the end of App School, so I think we will take a look at that towards the end of App School. All right. Anyway, okay, so this is what a scry will look like. It'll have information about the vein, or so it'll have type, it'll have vein, it'll have kind of request into the vein, and there's a lot of different kinds of requests into different veins. You know, Clay has like 17 different kinds of requests you can make because you might want to know file permissions, you might want to know the desks that are installed, you might want to know things about the state of the vein itself, right? Like you're actually asking things about Clay or maybe the underlying system, or, you know, whatever, right? Like there's a lot of possible things that you might do, kinds of requests that you might make here. And then it has some sort of path, and you're generally using your timestamp and just say, give me the most recent value, whatever this is. Now, I don't think graph store, I used to use graph store as my example for doing this, and that's not going to be on a fake ZOT anymore. So another thing I might be able to do, should be able to, I guess I'd actually have to know what my yeah, I have no idea what my endpoints are in talk. So maybe we'll take a look at that in a minute, actually crack open the file and figure out what's going on there. For now, let's go back and take a look at what's going on with our different veins, just so you, like I say, you know what your options are when you run code here. Yeah, so this is kind of information overload, but it's a good reference card for you to be able to come back to and say, you know, what are the kinds of things that I'm keeping track of here. Okay, so AIMS is our networking system. This refers to ship-to-ship communications. All right, so this is the way that we're going to do that. Andre, you have a question about writing to a file. I'll come to that in a minute when we talk about Clay, okay? So all of your ship-to-ship comms, installing things, whatever you're doing, this takes place over AIMS. Most of the time as a user writing apps, this is handled automatically for you. You don't ever need to actually worry about, or, you know, am I end-to-end encrypted? Do I have a connection to a particular ship and so forth? AIMS handles that automatically for you, which is good, right? Like this is what we want an operating system to do for it, is to make it so I don't have to set up my own networking. So it, you know, it takes care of packet construction and encryption and decryption and connection and routing and all this other stuff, you know, authentication, you know, are they actually who they claim to be? All of this stuff gets handled by AIMS. You will use Bane occasionally. Now, Bane is simple. It's a small vein. We call it the timer vein, but basically it's a clock. And so if you want something to happen at some time in the future, then you set basically a wake up notification to Bane, and very slightly after that wake up time, you're going to get a notification that, okay, it's time to do the thing that you wanted to do. So for instance, you know, we might write an app that needs to pull a internet data source every 30 minutes. So you'd set a timer that every 30 minutes it kicks off this process and attempts it again, and just, you know, is always running that so you have up-to-date state in what's going on. All right, Clay, you've kind of messed around with Clay some. I should actually delete that. The 2 GB limit is now gone. Clay is what we're going to call a typed file system. So I hinted that it's kind of like version controlled, because you actually can see the history of the files, the versions of the files are there. Every file has what's called a mark. And a mark is essentially, it's kind of a type, and it's a set of rules that shows it how to transform from one kind of thing into another kind of thing if it has the right shape. So Urbit likes internally to represent everything as nouns, but maybe the data that you're working with are better dealt with as like a JSON object, or maybe they're better dealt with as a chord or a tape or a list of chords or a list of tapes. Or maybe there's some sort of custom update data type that you wrote for your agents to talk to each other. What a mark does is it basically says, if there's a way defined to do this transformation, I can do this transformation. If I receive a noun and I can turn it into the shape of a JSON object, then that's a valid operation. And so this is what marks do for you at the level of the file system. We also use marks internally for marking other kinds of data. We talked a little bit about cages last time, which is a pair of mark and base. As a way of like data validation. So marks do a few different things in the system. The thing they do on the file system is they define the way in which data are represented. So for instance, this means that if you want to host an MP3 file on your ship because you're hosting a website and you want to be able to play an MP3 file, this would mean that you would have to have some kind of mark that would load an MP3 file. If you tried to include it on your desk without it existing, you get some kind of error that it doesn't exist. So you'll run into that. The yard desk, which we pushed very recently, actually, and we'll probably take a look at in one of the later lessons, actually has essentially all of the common MIME types included in it. So if you want to host a WAV file and an MPEG movie, then there are marks that will handle this for you, and you don't need to worry about anything special in setting those up or hosting those. Now, we can write to a file. We're not going to do that through scries, because scries are requests for data like, show me this information. That's all that's going on with a scry. So if you'll go back to the early concept here, a scry is not passing a value. A scry is simply saying, show me this result. Show me, give me a number, give me a value, give this directly to me. If we want to create a file, what we're going to do is we're going to pass a move to Clay, requesting for it to create a file in a certain path with a certain set of data as its contents. So this is the way that we would be able to do this with Clay. In practice, we often don't end up doing this from user space because most of the information that we store is more conveniently used in Gall in our agent state anyway, rather than trying to pull it from a file. So it's supported. You can do anything you want to with it. It's not a common pattern unless you're doing like a data export in Clay today. All right. Dill, not much to say there. It just handles your terminal session, your web term, whatever else is going on. Air is your HTTP server. So most of the time, when you're hosting things from your ship, you're opening grid or landscape or groups or whatever you have. Air is what's doing all of the work for that. What is meant here by data subscription model is that Urbit prefers what's called pub/sub, publish, subscribe. And so what you'll do when you create an agent, and we'll do this next time, is you'll say, I want to subscribe to a path with a name like Faz, I guess we have Alpha, Bravo, Charlie. I want to subscribe to Charlie at the path updates. And then anytime Charlie makes an update, it will send a gift back to everyone who subscribed to that path, and they will receive information about, okay, what is my current, what is the current state of my friend's Charlie, like the Charlie that's running on this other ship. So we'll come back and forth from those. User space. So Gall does what's going on here. I say persistent daemons with a standard form here. You know what that means at this point, right? Like every Gall agent that you write is a door that takes its sample is your state, and whatever else you do is basically taking place in this standard form. That you have 10 arms, and your kinds of interactions that are available to you are done this way. Client services. This is Iris. Iris is not used a whole lot. This would be if your Urbit ship were acting like it were a browser for someone else's website, which you certainly can do, but it's not a common design pattern yet. I've seen people try some interesting things with trying to deal with server behavior, loopback addresses, these kinds of things. Amadeo and I were working for a while on like how would you run a CDN, a content distribution network, maybe using Iris to host some of the information, or run oh, what's the word for it? It was a load balancing system that I was working on. Anyway, so anyway, Iris isn't used a whole lot, but this is like if your Urbit were acting as a browser functionally. Jail keeps track of azimuth state, so it keeps track of the public key, someone else's public key that you know, or the ability to look it up if you have not previously communicated with this shit before. So this is essentially how you encrypt and decrypt values is using jail here. As a vein, like Bane, it's basically complete. It's not really clear what else you would ever need to change to make this work correctly. Con lets you use threads, which are transient, lightweight user space processes. They're sort of like single-use agents, kind of like a more powerful generator in a way. We like to use them where things are liable to fail. So if you're making a network call, for instance, network calls don't always go through. They might fail for a number of reasons. And so threads are the model that we're going to use for that. So we'll get to those, I think, in App School 5. And then Lick is another brand new vein. It's actually not even on your ship yet, because it's going to come out in the next runtime version. This is an external interprocess communication vein. And so this lets you do things like talk to external hardware, or have external hardware talk back to your runtime, to your var. So there's some really interesting things that can be done with this in using Urbit as a front end, or excuse me, using something else as a front end to Urbit, using Urbit as a back end for something else. There's an example out there called Slick, which is Urbit has a snake game, where you can mouse around arrow key around and play a snake game, and where it's hooked up to a Python front end. And so it's running on Urbit. Urbit is keeping track of the state, and Python is simply displaying the state and handling the input output at any given point. So there's some fun things that can be done here. Hardware control, Internet of Things, possibilities like that'll be opened up by this as well. So that's an exciting vein. Also, you'll notice like Con, like these are actually small veins, right? There's not a lot going on with them. All right. Now, let's see, we can take a look at some more scries. Let's do that. I think that'd be kind of valuable at this point, is just say, what does it look like to just pull in information and play with it, like get these values. All right, so normally whenever you write a scry, you're going to need to know something about the data format that it comes back in. Now, you can always receive a noun, but you might have to make some intelligent guesses about like what kind of thing it is if you do this, if you just get it back as a noun, because a noun doesn't have any other type. Like there's nothing going on with it to help you figure that out. So you'll go look at the Scry API reference. For every vein, there's a page on developers.urbit.org, which has that information, and just find it, see what it is. So for instance, if I want to know from jail, what my current login code is, right? Less code. This is what's actually coming back. So I would have to type lidlet, tampled, pilex, ridrup. This is the default Zod code. If anytime you start a fake Zod, it's going to have the same login code. This is it. So you'll always see this value there. Get this out of the way. You don't need the sig at front. So actually, if we cat, let's see, let's cat, I guess this would be gen code hoon. Then we can see what's going on here. Let's see. So this is a say generator. You will have seen say generators in Hoon School. It does accept now, entropy, and then the beak being sort of your current like tis, or excuse me, faz, tis information. It's going to return a tang. We haven't really worked with tangs yet. Tangs are a kind of a formatted text output. So we will run into them as we get deeper into the Urbit system, but not yet. Don't need to worry about them yet. It's just that this is basically, this is text coming out. And the core of this is this scry right here. There's a .ket, pat p, send j, and it's going to take our current ship, code, our current timestamp, and then our current ship, which is essentially what I did right here when I did it manually like this. What does Scott do? Has anyone worked with Scott before?
Is that a
Okay, so
typecast?
it's not exactly a typecast. Close. It's a sort of a write to string. Like if you've worked with Python, it's sort of like representation or string. It's not exactly a typecast because, of course, you know, the pad of hour is in this case 0 because we're on Zod. So it's not, yeah. And the pad of this is whatever, you know, the pat UX. You can see the ASCII characters there, looking at that SIGZOD. But this is how we convert a value to text. So your normal pattern with this is, you know, you're going to give it the type as a term instead of as a like you don't do pat p or pat da because that's a gate, right? Like that's actually a mold that's trying to, you know, that's a operative function. You get the name of the thing and then you give it the value that you want
And
to
these
do.
are odors, not types, right?
What's that?
Are they called odors?
Yeah, I think the technical name for these is an odor, and I think together this is a dime. Anyway, there's some technical name for like what we're calling this piece here. I think this piece by itself is an odor. I think you're correct there. And we actually have, you know, flexibility to do some interesting things where I can put information in one format and then it will interpret that value as an atom and then turn it into whatever other format here. So, you know, it's a 10 gazillion days since whatever the 0 of pat DA is in this case. So we're going to use Scott anytime we need to get from a value to text, and we can do it by type, right? And so it doesn't care, right? It's happy to take 0 and turn it into something. It's happy to take some timestamp and turn it into a pat p. Like, okay, great. There's a weird comment for you. You know. So it just does that transformation for you. However, it's also very common to see scow. All right, so what is Scow doing instead of Scott?
Is that turning it into a chord instead of a
Not a chord,
tape?
tape, yeah. So this is, so Scow is to a tape, Scott is to chord, Scow is to tape. I know of no mnemonic that actually does this, except just remembering that this is what happens. You know, it's one of these weird parts of Urbit that sort of feels like overspecified, but in some ways it's actually kind of nice because I can just swap out this value and you know, get whatever kind of thing I need here, right? There's as a SEN-UD, here's as a single precision floating point number, which actually doesn't make sense. So let's try a quadruple precision and see if that works. Yeah, so there's the value as a quadruple precision floating point number, like whatever that means, right?
Oh, okay. So it's the output odor that you're passing in, and you can pass in an atom of
Yes.
any type.
Yes, you can give it any data value, and this is just going to get turned into a pat. So this is just going to get turned into a raw atom, whatever that value is. And then, yeah, this is the target output odor in those cases. Let's see. We have talked about. We've talked about types, like vase, cage, card. We did that last time, so we don't need to get into those. Okay, let's talk about this. All right. So when I run less agents on send base, it gives me a list of my agents and which agents are running and which agents are not running. All right, so let's actually open up the file base gen agents. All right, this is not a very complicated file. And the reason it's not a very complicated file is because it's wrapping all of its complexity inside of this gate in a library called hood. Now, a lot of times this is what's going to happen is you're going to look up some value and you're going to be like, oh my goodness, I'm going to have to go dig through and you know, find, okay, where's hood, you know, so this is a FASHEP. So if I want to find this, I have to go look up Sir Hood and look for, what was that, git? Oh, what was it called? That was, I better write this down before I get deep into this. Git apps have. Copy that. And hood. All right. All right. Git apps have, find which apps Gall is running on a disk. All right, this is where I wanted to get into the scry that's happening internally here. So this is a gate. It accepts our current ship, our current desk, or you know, a desk, and a timestamp. And it's going to return a list of dude, which are agent names, and whether or not they are currently running. And the way it's going to get this information is a .ket scry with GE. What does this syntax here mean? GE less. You probably have not run into this because we've been avoiding it in the early Hoon School and working with things. But you will find, you know, we start to run into it now. So this is one of these other weird little shorthands that Hoon provides. So some value, you know, some name, less, and then a value basically head tags a cell with that name. So we'll run into this. So GE less is the same as saying send GE and then a space there. So if I'm going to run this here, I'm going to need a set of, whatever a dude is. Do I know what a dude is? See if I know what a dude is. It's a gall dude. So that's actually good because gall should be in my current namespace. And I can use that. All right. So this is a set. You remember sets, right? So sets mean that everything occurs once in the set. They don't have an order, but it's just sort of a bag of things, right? There's nothing else going on. It's a bag of things. This is the type I'm going to get back from this. So now I give it a send GE. So I'm scrying into gall with the type or care of E, and then I'm doing it at some path. So I could do tis, and then it looks like it wants a buck at the end. It's just kind of its default filler. Okay. So I'm getting back my dude and my live. I actually wonder if I could just do a pat TAS. Would that work? Yeah. And I could actually even simplify this further. Right. So this is, like if I know the return type that I'm getting back from something, then I can extract that information. Now, let's say I want to, if we bar install information, we bar install a desk, and that desk has a desk.bil file. And the point of a desk.bil file is to show what can be run, what should be started when a desk runs for the first time. All right, so if I spit out the contents of bases desk.bil, it gives me this list of just this list of agents that I have here. If I were to do this to alpha, then I would see alpha. If I were to do the bravo, I would see bravo. And so, you'll notice that it actually is parsing it, right? Like we didn't write this. We wrote, sig cell alpha, sen alpha ser to write this out as a list, but it's processing it into whatever information here because of the mark at the end, which just gives you the display of the values. Now, sometimes I want to have more control, like more fine-grained control over my installation than I'm getting otherwise. So we can think of desk.bil as a register of agents to start when installed, but it's also a list of agents which can run on a given desk. All right, so if you have something, if you want to run an agent on a desk and it's not in desk.bil, you can't actually start it in gall. Like right now, that's a hard limit. So desk.bil is considered a mandatory file when you're doing this kind of development. However, if something is in desk.bil, you want to turn it off, you want to turn it on, you have some tools to do this. So in the first place, you have suspend, which stops an agent, keeps state. All right. There's nuke, and let me get rid of which because, all right. All right, so bar suspend keeps your state but stops the agent from running, which means it can't accept new pokes, new subscriptions, whatever else. It means gall just keeps the state. It knows the structure, but it's not going to process any inputs that are directed at that agent. Bar nuke means you stop the agent, you delete the state, can't do anything else with it. You're going to use this a lot in development because it's an easy way of resetting and making further progress. It's also convenient sometimes to use rain. And so with rain, we would say something like bar rain, and then the desk name, and then we would give it a, are we turning it on or off? And then the agent. So we're saying, on desk, start agent or, on desk stop agent. And so this lets you, this should be equivalent to bar suspend. This should be equivalent to revive. They've moved things around sometimes, and so I don't know if they're always exactly equivalent to each other. But broadly speaking, they should be equivalent. I should include bar revive here too, which is but you will have to run bar install at least once to just sort of register all these things in the first place and tell Gall, here is a desk that is valid to use. All right, like do things with it. Like you can run things on this. And then, like when I did send GE, this was the list that on this particular desk, here are all the things I know about that can run on this desk. So what am I going to see if I give it a different desk? So let me suspend alpha. Now, if I run this, I get that alpha is not running. And if I try to poke alpha, call alpha less debug, for instance, I just get a poke. I don't think debug was even working with it, but it just gives me that it's not running right now. So bar revive, send alpha, restores that state for me. And then you notice that immediately I got this debug response. One of the interesting consequences of Gall is that you can peek or poke at an agent. Well, I shouldn't say that you can poke or peek at an agent, like scry at an agent, but you can poke at an agent, and those pokes are queued up. And then when that agent actually starts, those pokes hit it at that time. So the agent wasn't running, but Gall kept on to the fact that I poked it using the debug generator. And as soon as it revived it, that poke hit it, and it gave me the output response in those cases there. And then it told me that it is failing for whatever reason. I don't, maybe I didn't have it installed for alpha after all. Bravo. Yeah, maybe I'm just sig-pamming the internal information. I think that might be what I'm doing. Okay, so there are some games we can play to tune this and get exactly the behavior that we need as we're starting to do this. Last time we used NewDesk to create a minimalist desk. NewDesk, the advantage is that it's clean, right? Like it's a clean, simple desk. The disadvantage is that you have to copy a lot of mark and library files to get it to work. Bar merge, for instance, bar merge new, or we'll do Charlie because we're going to do this later. Charlie our base. This makes a copy of base and names it Charlie. The pro of this has all mars or lib files. The con of this is that can override system if not careful. And what that means is that you actually need to edit desk.bil immediately. Or otherwise, when you update this desk, it will supersede your base installation because there will be 2 copies of ETHWatcher and 2 copies of the other, Acme and Lens and the other things that are running on the base desk. So that's kind of a pain. But we'll run into both of these as we work on these. Neither one of them is really completely satisfactory at this point. I think long term, or even maybe medium term, I think we could probably get it done pretty quick if there's the impetus to do it. It would be better to just update NewDesk so that you can do some basic things with it. Like right now, it includes the ability to basically have a text file on the desk. But even if you add a desk.bil, you have to go copy in like a mar, mime.hoon, and a couple others to get that to work like we ran into last time. So ultimately we'll probably fix that, but for now, that's the thing you have to keep in mind when you're starting a new agent. Which you'll probably do more of in app school than in the future, because in the future, you'll probably have something you like to start with, and you'll just, bring it in from GitHub, copy the desk in from GitHub, and then you won't be starting from total scratch like this. All right. Let's see. What questions about Arvo or Gall or Scries or paths or anything else remain at this point?
I just have a small question. When you were scrying with Gall, what was the you used sen GE? I didn't quite understand the E after the Gall like call.
Yeah, so the first letter is the vein. So there isn't currently an H vein. So you have A, B, C, D, E. There's no F. There's a G. There's no H. J, K, L will come out when lick is around. So right now, so the first character is always the vein. The second character is what's called the care, C-A-R-E. And this tells it the kind of information, it's basically, it's an internal designation for like what you're requesting. And these can get very complicated in the case of in particular, Clay. I think Ames has quite a few as well. Like Clay, let me see. Oh yes, I do. I have the list of cares for Clay right here. Ha, my message is too long. Let me try. See if I can do half the message at a time. So you can see here that, Clay has so you could do a CA, a CB, a CC, a CD, a CE, a CF, a CP, a CR, and so forth. And so that second letter is the care. And it will vary by vein. Some veins like jail and lick and con do not have cares at all. You just scry into the vein like senj. Most veins have at least an X, like if Ames X, AX, AY, and a Y. Most veins have an X and a Y, and then a couple of veins like air and Clay have a lot of others as well. That's what that second character is. And that's just got to look up the docs to see what those are most of the time. All right, another question. Say a file format has 2 JSON marked. Does that mean we never have to worry about parsing a blob of bytes for that again? Yeah, essentially. So there's a caveat, right? So in Hoon, we're actually going to do we're going to parse and then we're going to reparse JSON. We're going to do this, I think, in 2 weeks. And essentially what happens is when we receive JSON, we can turn it into a Hoon noun. So JSON comes in as text in the right format, and we turn it into a Hoon noun. And then we're going to reparse it into basically the values that we actually want out of that, right? Like we're getting a JSON because there's values inside of this data structure that we want. So the parser converts it to a noun, a regular Urbit noun, and then the reparser is going to extract those values for you. Once you've written so parsing's like one step, it's built in. Reparsing means you do have to write this once, and this is very often done in the mark. It does not have to be done in the mark, but it's often done in the mark. Once that's done, you don't have to do it again, as long as no one changes format. Reparsing is kind of a pain. It's weird. It's almost a DSL, a domain-specific language inside of Hoon. It's kind of hard to work with. But there's a tool that Litlep Nibite wrote recently called John that's a generator that you can give it an example of the JSON that you want to parse, and then it'll output in text the equivalent reparser for you. Then you could copy that and paste it in your code. And you'd have to make a couple modifications, but it's generally speaking, it makes life much easier. Question 2, how does HTTP work? Can a ship send or receive requests on the open internet? Yes, like it is an HTTP server. So I can send put, get, and post requests normally, and I can receive them as well. And so this is what you'll be doing when we actually start working with Air directly later on. Let's see. Okay, no other questions came up in the meantime. So, like I said, this is kind of a more abstract one. We're going to get back into code wrangling next time because we're going to start building agents that have non-trivial state, 2 can start talking to each other and poke each other and subscribe to each other and so forth. So we'll start to do different kinds of things with it, or agents that aren't even the same agent. Like there's like a database agent and then like a database watcher agent, and they would be able to talk to each other. So we're going to start getting into that next time. Jack, do you want to comment on office hours?
Hey, yep. I just released office hours times, posted it in the admin channel, but short answer is that they're going to be Mondays at 5 p.m. Eastern and Fridays at 1 p.m. Eastern in the Hacker House in the usual place in the pirate room in top right. So if you just came off of Hoon School, these will be the familiar times from Hoon School, except I'm no longer doing the Saturday hour. But yeah, Monday at 5 and Friday at 1 Eastern.
Awesome, thank you. Let's see, question. Say you'd want to know if an agent is running first, then take information to persist and extend on your app. You would do it via script. Yeah, so for your first step would be, check, is the agent running? And if it is not running, then presumably you'd want to output some sort of error message. And so you'd probably handle this in your on init or your on load arm. You're writing something that needs to work with PALs, for instance. You're going to notify people, hey, you need PALs installed to make this work. Also, you would need to copy the SIR file of the other agent data into your own app. Yes, so there'll be a SIR file, a structure file. We haven't really messed with these yet, but we're going to start working with these as we do this. So if you want to work with the particular data of a given agent, then you need the structure file of that agent, right? Like you actually need the information that makes it legible to your app to use and work with. So we will start doing that, but it also means you're going to have that structure file on your own desk, because you can't use FAS runes like FASLess or FASHEP with files that are not on your current desk. You could scry and read them, but you can't directly build them and put them in your namespace in a straightforward way. So, I mean, that's kind of the advantage of a desk is a self-contained installation. The disadvantage is that, you have to sync the information manually to distribute that desk correctly and get things to work. Oh, hi, puppy. All right. Sounds good then. I'll get the homework out to you in the next 24 hours or so. Get this video posted and then talk to you next week.
All right. Thanks, Neil.